Hello, welcome to Electromagnetic Induction, video number 2, Lenz's Law. Last video we looked at Faraday's Law, so we learnt that we could generate a current in a conductor if we applied a force to it and moved it through a changing magnetic field. Now Lenz's Law is an addition to that, and it explains why we can't just generate electricity for free. So Heinrich Lenz, 1804 to 1864, that's what he looked like, and his law states the current induced in a conductor by a changing magnetic field is in such a direction that its own induced magnetic field opposes the change that produced it. What's that mean? Okay, because we're inducing a current, and we previously learnt that any current in a conductor generates a magnetic field. That's why we had the right hand grip rule, and there's an interplay between the generated magnetic field and the magnetic field that's causing the current to be generated. So we're getting two magnetic fields and they oppose each other, and Lenz's law means that nothing's for free. Basically you have to do work. Because the generated magnetic field opposes it, you have to force it, just the same as you have to force two norths together. It's very similar to that. You actually have to do work to get them to get two magnetic fields that oppose each other to do things. And so in terms of a solenoid, what we're doing here is just showing how Lenz's law applies, and it's a little bit conceptual, and so we'll also demonstrate this in the lab as well. So let's have a look here. We're moving a north in to a coil. So there's our coil, and that's just connected to a galvanometer, so there's no current in the coil. If this magnet is stationary, this coil does experience a magnetic field, because you can't turn the magnetic field from the bar magnet off, but it's not a changing magnetic field. To make this coil experience a changing magnetic field, you've got to be moving this bar magnet. So if we move it in, so we're moving a north in, the current that's generated in this coil will generate a magnetic field to oppose that. And so to oppose a north going into the coil, it generates a current in such a way as to produce a north there. So the field lines are coming out here, opposing the field lines here. And so we can then use the right hand grip rule on this solenoid, and we recognize that the current must go across this way to generate a north there. Okay, and so the needle will go one way. Now if we do the converse and we take a north out of the coil, Lenz's law tells us that we'll induce a current because this coil is now experiencing a changing magnetic field. Effectively it's experiencing a collapsing magnetic field, whereas here this coil was experiencing an increasing magnetic field as we brought the north closer to it. So here we're pulling a north out, so now the current will be induced to oppose that. And what will we do to oppose it? We'd have it south here to try and attract the north back in. And so the current here would be induced using our right hand grip rule in such a way as to flow across or in the coil like so, across here. And so we're getting a different direction from what we were generating here. Okay, so that's Lenz's law for a solenoid. And again, here a north is going in, so the current will be generated in such a way as to have a north there to oppose it, so you have to actually do work. And when you're pulling it out, a south, and so the current will change directions. I'll also demonstrate this, but now you can do some questions as well, and they'll be in the OneNote for you and in your workbook. So let's have a look at some of the questions I'm going to ask you to do. Just make sure that you understand what's happening in them. Here's our figure, a conductive metal square coil. So coils don't have to be round, they can be square. Square makes it a little bit more convenient to work some things out. Position within a magnetic field. so which is into the page. If the sides are 5 centimeters and it's moved at a velocity of 8.5, calculate the voltage induced across each of the sides of the coil. So that would just be using Faraday's law, and whether an induced current will flow around this coil as it is moved. Explain. So here, just recognize that these bits of the coil won't be cutting magnetic field lines, so have nothing to do with it, and then you've got to use your generator rule to work out the direction of the current in each of these parts and then determine whether a current will flow. But you can work out the EMF for the various sections. Alright, so this one you've got to do. Here you've got a small solenoid and a large solenoid. Large solenoid is attached to a galvanometer, and here you've got a voltage supply, resistor, so you're just running a current through here. Whenever the switch is turned on, a current will go through this coil, and so that will effectively make a magnetic field. So this coil will go from having no magnetic field to, when we close this, to suddenly the magnetic field just doesn't appear, it expands. And so this coil is experiencing a changing magnetic field, but if the switch is stayed on, that magnetic field expands in an instant and then just stays the same. So what's going to happen? And then if you open and close it, what's going to happen to the galvanometer? So just think about that and have a go at those questions in your workbook. Don't forget the generator rule, okay, that we've got. Your thumb is the negative charges, your force is your force applied, and conventional current or positive charges is going in that direction. So you'll find if you go on the internet a whole lot of different rules. This one uses your left hand for the motor rule. I'd stick to the right hand rule and just remember whether or not you're using the motor rule or the generator rule. You can use the Fleming's right hand rule or the Fleming's left hand rule, your choice. And so let's have a go at these. So here's a conductor moving through a magnetic end. The question I ask you is which end will become positive and which end will become negative. So just pause it now and have a go. Alright, so you've had a go. Using your hand, I'm looking at the picture now, so what I'm doing is fingers into the page, palm is in the force that's being applied, or the velocity, and so this will be my negative end, so the negative charges are going to go that end, and the positive charges to that end. Let's do another one. So which way is the current going to flow in these parts of the coil? Because we're doing work, we're turning a coil in a magnetic field, so this bit of conductor is experiencing a changing magnetic field. So pause it and work out what you're going to do. Pause. Okay, don't forget to restart it. And so did you get current going down that way? Now this is conventional current, and that way. Okay, here we have another one. So I'm going to do it. Magnetic field is going, I'm looking at the screen now, so I'm going like this, and the velocity is going down that way, so I'm going to say this end negative. Yeah. Now that's a potential difference. So now we have a current, so which way is the current going to flow? And let's indicate conventional current. So pause it and have a think about it, and then restart it. Okay, did you get this? Hopefully you did. Now this one again, another scenario, slightly different, but try it again. So pause it and work it out. And did you get that way? Now if you're not getting consistent results, it means that you're not quite getting it, and I suggest that you rewind and start again at the beginning. Okay, will a current flow? So here we have a square coil moving through here. Watch our answer. We can work out that the current will, there'll be a potential difference across there, or an EMF and an EMF there, but the two EMFs are effectively in the same direction, so no current will flow, even though it is cutting field lines. This coil is getting rotated around this axis, so will a current flow? Yes or no? Pause it and work it out. Okay, Get the answer? Yes. Okay, in this one, which one will become positive and which one will become negative? Should be getting all these correct. Ready for the answer? There we go. And in this one, which end is positive and which end is negative? Remember, we're only getting a potential difference across the two ends, or an EMF. There's our velocity, there's our length. That should be our positive, that should be our negative. What about this one? In this case, it's moving that way. Are we going to generate any magnetic field? No. Now, what about these three scenarios? Are we going to generate a EMF across the ends of this conductor? Well, in each of these cases, there's not going to be any EMF because no field lines are cut. One way of doing it is to use two pens or your finger. Have the pen as the field lines and your finger as the conductor, and not cutting anything. Not cutting. Alright, that's not cutting, that's just getting in the way. Alright, moving it this way from D. Okay, it's not cutting. And what about this one? Cutting? Not cutting. The only way we generate a EMF is if we cut field lines. So here we have some solenoids. So this is a cross section through a solenoid, and you're asked to determine which end is north and which end is south, and which way will the current flow in the loops or the coils. So into the page or out of the page, crosses or dots on these in these circles. So we're pulling a north out, so we're going to get a south here and a north here. Then we use our right hand grip rule to determine that that's the direction of the current. So have a go at this one, pause it. Okay, you ready? Have you had a go? So to oppose a south being pulled out, we have a north there, and so the current's going to go in the opposite direction. Into the page there, out of the page there. Alright, which way is the current going to flow in this conductor if it's moving like this? Are you ready? Pause it, have a go. Hopefully you got the right answer. Into or out of the page? Into the page. What about this one? Into or out of the page? Wait for it. Out of the page. And this one? Okay. I sort of jumped ahead there. Hopefully you consistently can work out why that is the case. And again, which way is the current going to flow in these wires? Up or down? So here we're pulling a south out, so we'll generate, pause it, have you worked it out? So we want to have a north there, so the current will go that way. Here we're pushing a south in, so we want to have a south there, so we'll have dots and crosses. Here we're pushing a north in, so we want to have a north there, so crosses there, dots there, cross there. Okay, in the next video we'll look at generators and how they actually work in the application of electromagnetic induction. Cheerio!